Hello and welcome back to Electronics 101. This is episode 3 where we talk about diodes and transistors, the tiny parts that build the entire digital universe. So let's dive into these two tiny components that quietly power our entire digital universe. These aren't just parts. They are the reason your phone wakes up, your laptop boots, or even why the internet works. So before building computers or calculators, we must learn how to guide electricity exactly where we want it to go. And to do that, we rely on the building blocks we discussed in earlier episodes, the P-type and N-type semiconductors. Keep that in mind because today they are going to come alive. Let's begin with the simplest controllers, the diode. So the diode is a one-way gate built from PN junctions. Let's look into it. It's one of the simplest devices in electronics. It has two terminals and one very strict rule. Electricity flows in through one side and goes out through the other side, but it cannot flow back the other way. And here's the important part. A diode exists only because of something we learned earlier, the P-type and the N-type semiconductor materials. A diode is literally created by joining one P-type region and one N-type region together. So this junction is what gives the diode its one directional behavior. The P-type has holes, positive charge carriers. The N-type side has extra electrons. When you put them together, electrons and holes rearrange themselves, forming what we call a depletion region. It's a natural gatekeeper that allows current to flow one way but blocks it the other way. So let's look at another concept, forward bias and reverse bias. This is how the PN junction responds. The diode's behavior depends entirely on how you apply voltage across this PN junction. In forward bias, you connect positive voltage to the P-type side. So this shrinks the depletion region. The barrier drops and the diode starts conducting. It's a green light. In reverse bias, you apply the positive voltage to the N-type side. The depletion region widens dramatically and the gate slams shut. And as with all silicon diodes, you need about 0.7 volts of forward bias before electrons finally have enough energy to cross the junction and let the current flow. That's why the diode works and why the PN junction is one of the most important inventions in electronics, because it controls the flow of electricity. But the diode can only enforce direction. To control current, amplify the signal or act like a switch, we need something a little more evolved. So let's look at that little more evolved component. It's called a transistor. So the transistor is basically two PN junctions and there are endless possibilities with that. The transistor is the heart of modern electronics. It revolutionized everything when it was invented at Bell Labs in 1947. And guess what? A transistor is built by combining P-type and N-type semiconductors in a very specific arrangement. There are two major types, the NPN transistor, where we have the N-type, then we have the P-type, and then we have the N-type, all put together. Then we have the PNP transistor, where we have the P-type, N-type, then P-type again. In other words, a transistor is basically two PN junctions back to back. This structure gives it something the diode does not have, a controllable middle layer that allows us to regulate current. So that middle layer is the base and it's the secret to everything that follows. So how does the transistor work? PN style, let's look at that. A transistor has three terminals, an emitter, a base and a collector. And the P-type N-type arrangement creates behavior that feels almost magical. So let's look at that. Think of the transistor as a water faucet or a tap. The emitter is the supply of water. The collector is the spout where the water flows out. The base is the handle, a tiny control point. So just a small input at the base changes how easily charge carriers move through the PN junctions, allowing a tiny current to control a much larger flow. So this gives us two incredibly important abilities. One, switching, which is the foundation of all things digital. Push enough current into the base and the transistor switches fully on. Pull it away and it switches off fully. So on is 1, off is 0. Billions of these PN junctions switches firing every second They become the core logic of your CPU. Let's look at amplification, which makes signals stronger. If you feed in a small but varying current at the base, the transistor multiplies it. This is how microphones make your voice louder and how radios boost weak signals. Again, all thanks to those precisely engineered PNP or NPN structures inside the transistor. So from diodes and transistors, we are going to logic gates and microchips. So if you zoom back out a little bit, diodes are simple PN junctions that enforce direction. Transistors are two PN junctions that provide control and amplification. So when you start combining these devices, diodes guide current correctly. Transistors act as ultra fast switches. Together they start forming logic gates like AND, OR, NOT, all those things. Etch a billion of these p-type and n-type structures onto silicon and you get a microchip, the brain inside every electronic device. This means the entire digital world, every computer, phone, router, server, everything, it all rests on the behavior of p-type and n-type semiconductors arranged into diodes and transistors. That's the beauty of semiconductors. I think you were able to connect p-type and n-type semiconductors with the modern uses and how microprocessors and digital devices have come into existence. So it's easy to be amazed by all these AI, smartphones and modern computing. But beneath all of it are two unbelievably elegant ideas. A simple PN junction that lets electricity flow only one way and a pair of PN junctions that let a tiny signal control a huge one. This is it. This forms the basis of everything else. Logic, memory, microchips, processors, they all come from these semiconductor foundations. Two kinds of silicons, p-type and n-type, two types of charge carriers, and two components that change the world forever. I think that should be a wonderful message to carry forward into our other episodes. I hope you enjoyed this one. I'll keep it short and stop here. Do come back for more. We'll go into the details of logic gates. We'll go into NAND gates, OR gates, and all the digital processing that we need to know. So do subscribe. Leave a comment if you have a question or if you like this episode. Yeah, tell me something. I'd like to hear from people who are viewing this episode. So yeah, see you soon in the next episode. Thank you for watching.